And so I don't actually have that open. What I have open are some other things. First of all, the textbook, and I'm looking at a little bit different, stop it, a little bit different view than what you have. We left off last time beginning to talk about relational algebra. Now, the other thing that I have open that I'm going to bring kind of back and forth is my OneNote notebook. And for my OneNote notebook, you know, I already had that PowerPoint pulled in from last time. And I've been updating a little bit, so I have to get back to where we are starting out. So relational algebra. Depending.
Question before we started, because this is about the section we just left. I ran into this on the problem. I think I already know what the answer is, but it'll help. Can a foreign key be used to make a composite key? I don't think the book doesn't say yes or no, but I'm just trying to go through the logic of.
Sure, you should be able to use any data to create a composite key depending on what you need, what your situation is. So part of that data could be any data element. So there isn't any sort of restriction on what data you can use to create a composite key. So you get that uniqueness and something that you can, the data that you can actually get to.
Right. Okay.
Access. So we've been talking about data and relationships and how we can have this kind of tabular format to view the information that we're trying to maintain. And all of that lends itself to relational algebra. In relational algebra, if you've ever had a class where they've talked about that concept before, is just applying mathematical logical operators to data, to sets of data. So it's very logical. It just gives us the opportunity to manipulate our sets of data and pull things out of our data that we want. And remember, that's the whole purpose of what we are doing here, is we are worried about creating queries and other pieces of data information so that we can extract data from a data warehouse, a database, and give it to our users for their use. So whenever we're looking at these relational operators, and we'll get into them, if somebody's not muted here, mute for me. Who we got? To mute them all. But whenever we are looking at this relational algebra, one thing that is an important concept is closure. And all that means is when I apply one of these relational algebra operators to a set of data, the resulting set of data is going to be a new set of data. Does that make sense? So I can take it and get something new out of it. So the relational operators that are available are many, and you could spend a lot of time researching them, but we're going to look at the most important ones, the most often used relational operators. So those are select, project, union, and intersect. And just real quickly, select is also called restrict. It's going to supply a subset of data. Let's take a look at it. If you scroll down or look at the next slide, this shows us some data. We have one table, and we're usually thinking about one table when we're talking about a select relational operator. So here's our table. We have this original data. We have a product code and some descriptions and prices. And when we apply this select relational operator to our data, we can come up with a new table, a result set. If you look at this first result set, we did a select all, so it's exactly the same as the original set, but it's still new, right? It's a whole new table in memory. Now, if we selected a specific thing, like we only wanted to see rows in our table that had a price less than $2, then applying that select criteria would result in just a couple of rows that met that criteria, right? So if I said, take this original data and just give me all of the rows that have a price of less than $2, I'm going to get those 2 rows back. Here's another example where we've applied a select and we've said, we only want to see rows where the product code is this certain value. And that result just gives us this 1 row. So it's just real logical. A select looks at the table and applies some sort of criteria. So if we're looking at a select, they say that that can be indicated using the Greek letter sigma. And in our textbook, they supply this as an example. So here I'm saying, and I think that I've got something chopped off just a little bit. There it is. And you guys, you could use this snipping tool to snip from your Zoom session if you wanted to get it off of what I've found for us out of our textbook. Or you could get it out of your textbook. But I liked having it kind of all together here for me, in my mind. So the Greek letter sigma, and here's an example using a relational algebra formula to say, I want to select all of the customers that have a customer code equal to this 10010. So it's like a shorthand formula approach. So that is our select or restrict. These relational operators, you'll see, apply pretty closely to some SQL terminology when we get to that. Okay, the next one is project. And here I'm saying I've got this original table and I want to project some sort of results. Let's look at the rules here. It's going to return to me, I love the way they say it, a vertical subset. So I'm asking for columns of data. So just a little bit different than the select statement, because with the project, with my original table, I'm going to be pulling out just every single row, but just specific columns. So that's why they're saying vertical subset. So here, if I want to project just the price from my original table, I'm going to see a new table with just that price column. Here I project the description and the price. My new table results in just those 2 columns. Lastly, product code and price. More meaningful table there, right? All right, so the project is indicated by the Greek letter pi. And here is a shorthand version of a relational algebraic statement saying that I want to project from customer the first name and the last name. And just like other algebraic functions, these functions can be combined. So I can take the output from one function and use it as input into another. So in this example, we've got that combination. We're saying, what here? We want to select customers where the customer code is this 10010. And then from that, we want to project just the first name and last name columns. So we've combined those 2 algebraic functions to create a result set that's just what we want. Questions about that one? Combining the 2. Next is the union. And if I back up in the presentation and look at that slide where they introduce it, They mentioned that the union combines all of the rows from two tables. So we can think of it as a merge. We're just going to end up with a result set that includes both of our tables. We are going to exclude duplicates. So we'll just have one row in our output for every row in our input. And the tables have to match. They have to be union compatible. So that means they have to share the same number of columns, and their columns have to be compatible domains. What's that mean? Their data types have to be the same. If I've got a date and a date, they're compatible. So union. Scroll down. When I'm looking at a union, it's pretty straightforward. I have two tables. As long as they have the same column, I can just merge them together. So union is denoted by the symbol U.
Just like in math.
Yeah, because it's just relational algebra. So here, looking at this example, I am saying that I want the vendor name from my vendor table, and I want the supplier name from my supplier table. And now that I just have two names, I can use the union operator to combine them because they're compatible. Now, intersect is a little bit of the opposite. So union takes everything and merges them together and eliminates any duplicates. Intersect kind of only gives us the duplicates, right? So wherever the two values in our two tables match, that's going to be an intersection. So intersect is denoted by the upside down U symbol. And here is the same type deal where we're saying, I want to project from the vendor table just the vendor name, and from the supplier table the supplier name. And then I want you to give me instances where you see the same thing in both tables. So that would be somebody that we buy things from and sell things to. So that would be give us that interesting information. All right, so we're just applying all of these wonderful relational operators to our data, seeing how we can affect the data that we're looking at. A couple more. Difference yields all rows in one table that aren't found in the other. Whenever we do a difference, our tables have to be union compatible. We have to have that joining capability to make that work. And then product yields all possible pairs of rows from two tables. Let's look. So the difference. It's denoted with the minus symbol. And I'm basically saying from table 1, remove all of the entries that are found in table 2. Give you the results. So our shorthand formula here, an example would be project the vendor name from the vendor table, project the supplier name from the supplier table, and give me the difference, just the ones that are only in the first table. So notice how in this one, the order of the tables would matter, right? Brady came in. All right, I thought I didn't, it'll be fine. Okay, next, the product. The product gives us let's see, what have we got here? Combination of things, kind of back up and see what they say. Yields all possible pairs of rows from two tables. So when I'm looking at the product, notice it's just going to kind of generate possible output. So we don't have anything from our first table that matches our second table. We're just saying for every instance of table 1, add table 2 to it. So in our output, we end up with flags like 3 times, once for each instance of that second table. So we can kind of explode out, multiply out our table. So the product is indicated with the multiplication symbol. And just like this example, a shorthand formula is just the table times the table. So some of these relational operators are going to be available to us using the SQL language, and some we're going to have to do a little bit more manipulation to get there. But if we understand how this relational algebra applies to data and works, we are so far along in understanding how SQL works when we get to it. So we've taken these relational operators, and for the SQL language, we've implemented them as joins. So when we're using the language that we get to, we're going to be seeing these different kinds of joins where we can get basically those different relationships back to us. I'm going to go down just a little bit. Hang on, sorry. All right, I had to double check. So looking at joins, one place that's a really good place for this is W3 Schools. So go with me to W3 Schools. And in W3 Schools, I want you to find the SQL course and just click on this joins topic. Because we're not ready to use this content yet. We're not going to get to actually coding SQL for another week or two. But I do want to get these pictures, and these pictures will be helpful to us. So if we could snip these pictures, these help us understand how these joins relate to our relational algebra. So an inner join would be where I am taking the data that occurs both in table 1 and table 2, right? A left join, if we look at this picture, means I only want the data in table 1. I don't care about table 2 much at all, but I might be adding a little bit to my output from table 2. But it's not really affecting what rows are output. My right join the same way. I want all of table 2 output, and I might be getting a little bit of information from table 1 for that output, but table 2 is actually controlling how many rows I'll have in my output. And then a full outer join is that merge type functionality where we're going to combine the 2 tables together. So grab this picture. Snip it. And you can get that text right above too if you like to add it to your notes. I just want that picture. Now, as you look at this, you'll see we have a little bit of differences in terminology because when we're looking at the W3 Schools site, we're looking at SQL actual syntax. This is how you do it. And in our presentation, we're talking about theoretical relationships and algebraic terms. So we do see a little bit of differences. You can kind of figure out which is which. And as you're reading through the information, always try to be visualizing relationship sets like that because that'll really help to keep those things in your mind. We'll look at that when we get to our SQL section. Now this divide operator, this one is really interesting. And the divide operator says that I have these two tables that am going to join together. But if I use the divide functionality, I'm basically saying, I want you to only give me the occurrences in table 1 of data that's in table 2. So we can see we're dividing this first table by looking at this product code and returning all of the customers that have any of those product codes in the table. So relational algebra is just going to give us that concept of how data is related. If I have a student and I have a bunch of grades, how do I know what grades in this grade table belong to what student? I have to have that foreign key, right, of that student code to be able to attach that grade to that student. And I'm going to use a join to do that, to say I want the data where the grade student code is the same as the student code, so that I can match those up together. So that relational algebra is going to allow me to do that. We'll be looking at that as we get into our SQL section a lot more. Now, to jump off from there a little bit, something else that's really important to relational database management systems is the data dictionary. The data dictionary and the system catalog are the warehouses for the information that defines our database structures. So all of the code that defines our tables and our relationships and all of the users of our database system, all of the information is stored in our data dictionary and system catalog. In our system catalog, we're going to have things like customer ID. In a customer ID, we might have a customer ID on our customer table. It might be on our orders table. We might have it in some table off someplace else that's in our payroll department. Should the customer ID that's off in our payroll department mean the same thing as the customer ID that we use for our customer table? Yeah, it should, right? Because we don't want to have that same name mean two different things within our organization or within our data dictionary or system catalog. So we use these structures to make sure that all of our development is following all of the naming standards that we want. We make sure we only have customer ID being used to actually hold our customer IDs. We don't use it for something else that's unrelated. So that would be a homonym. I use employee ID incorrectly. And a synonym would be where I do have a customer ID, but I had some developer that decided it should be some other name. So instead of calling it customer ID right here, we're calling it customer partner number because they thought that was a better name. So now we have this one table that doesn't conform to our standards. It uses a synonym, a different name for something. So we want to make sure we avoid those. If we've got a customer ID, let's use customer ID as that name across our entire organization, which could be really, really large. So the data dictionary and system catalog will help us do that. And we're back to relationships. And I think you guys have seen it enough. You know it, right? Okay, you've built so many diagrams, you know it. One to many, one to one, many to many, many to many, bad. Many to many exists all over the place in the real world. Here's where they actually describe it. Just gave you a few problems over it, last chapter. So here we have a one-to-one relationship. One professor can be the chair of one department. We don't let them be the chair of more than one department. Now, most of our relationships in the real world are one-to-many or many-to-many. That's just the way things work. So here we have that example of a student who has classes, right? If I'm looking at my overall table structure, all of the students that are in my student table, I have a whole bunch of students. right? Each of those students could be taking a whole bunch of different classes. So that's one student could have many classes. On the other hand, I have all these classes over here, and one of my classes can be taken by many students. So we've seen that's a many-to-many relationship. Many students, many classes. And we can't support that logically in the real world in our data structures because we just don't have any way to keep track of all of those occurrences. If I sit down and say, okay, I'm going to keep class number 1, class number 2, class number 3, class number 4, class number 5 on my student table, that would get annoying really fast. Or if I said, well, I'm going to keep an array of class numbers on my student table, then how big is it going to be? What do I do to organize it? It's going to be a big mess. So the only thing, the best thing to do is to resolve that relationship by creating a link table. So my enrollment table here is going to link a student to a specific class. So now, if I look at my enrollment table, I'm going to see student ID 1, class ID 1, student ID 1, class ID 2. And I can look at that student table and see that student 15 times, once for each of the classes they've enrolled in. And when I am viewing a class, I can look at that class information and easily see all of the students that are enrolled in it. That makes sense? So whenever I'm looking at the database, often I'm going to be looking at it from a class point of view. And I'm going to be looking at who all is enrolled in that class. Sometimes I might be looking at it from a student point of view, who all is enrolled in that class. I have the option of looking at it from any different aspect, right? Because the way it's set up now with that link table, I can always logically find the information that I need. Now, does that make sense? Ask questions. Do we have a good example here? Not too much.
So the only question that I can think about on that is the link table, really the only data that needs to be in the link table would basically be the primary key from both of the other tables. Would that be about right?
Right.
And it wouldn't need anything else.
No, I shouldn't need anything else. Let's think about it from an Excel point of view. So if I have my first Excel sheet, that is my student data. And let's say I'm going to have an ID and a last name. Let's put some stuff in there.
You want us to be making this with you?
Yeah, go ahead and make it with me. Let's try it. So you won't be so bored. I'm not very good at coming up with names this morning. So I'm thinking short and sweet is where I am. So our student table is pretty small. We'll have a student ID and a last name. We probably would have some additional columns. Now let's create a class table or a class sheet. So I'll add another sheet here. Seriously, click. There it goes. And I want this one to be class. So I'll say class number 250 is database and 130 is web dev 1. And I'm not being fancy here at all, just trying to put some data together. So now that I have these two tables, if all three of my students have enrolled in the database class, how can I update this class table to show that? Can I just start typing in those student numbers? Let's see, I had student number 1 and student number 2 and student number 3. And see how that's not going to work over time? Because if I keep adding more and more students, I'm just going to keep going across and across and across. And how is my understanding of this data going to be enhanced by that? It's not. I'm just going to have this huge list, potentially hundreds of miles long over time, of students that are taking that class. Conversely, if I go to my student table and I say, how do I know what all classes student ID 1 has enrolled in? If I just add these class codes to my student table, again, I'm just going to keep going on into infinity, and it's not ever going to be making sense because it's not a limited list. I don't know how many. I could just keep going on and on and on forever. But if I make my link table, let's make it. My click doesn't want to work because I got to click somewhere first. And so I say this is going to be my enrollment table. I can say then that student ID 1 is in class 250. Student ID 1 is in class 130. Student ID 1 is in class 131. And then I could start with student ID 2. They're only in class 130. Student ID 3 is like in 250. And I could have another entry here for student ID 1, right? Because there's nothing that says they all have to be together in order. Would be convenient for me if they were. So that link table takes, yes, the keys from both sides, my student ID, my class code, and brings them together in just a plain list so that I can use that list to make that connection.
So link table then is made of two foreign keys, right?
Basically.
So then does it in itself have a primary key?
Well, that's a really good question. Do you think that it needs one?
It does.
It does really, because the best performance from our database is going to occur if we have a primary key. But we would have to make it a combination of those two columns for it to be unique across our table. Right?
So that makes sense. So the primary key is a composite key of the two foreign keys.
Mm-hmm, mm-hmm.
Okay.
Does that make sense?
Yes, it does. That helps because that's kind of a repeating theme that was kind of going on in some of the problems.
Uh-huh,
That the textbook is not. I'm not saying it's not purposefully vague.
Right.
But I don't know that it allows you to think through and answer some of that.
Yeah. It's kind of an implied topic.
Right.
So the other question that I've got about this, and I don't know if this might sound stupid, but I just want to make sure that this makes sense. In some of the problems that we had in chapter 2, they would show you tables that existed and say, what is the relationship? So the thing that you imply out of that is you're creating a link that doesn't exist, but you're just creating it to explain it. Does that first assumption make sense? Because the question is the link table an actual table that has to be made, or is this something that we use to describe a relationship? Does that make sense?
Right.
So is it actually a table that does have to be made?
Yes.
Okay.
So if we're just describing a one-to-many relationship, we are not talking about creating another table to support that relationship. But if we have our many-to-many, to resolve that, we have to put that link table in between, and we have to.
Okay.
So we don't.
It is like not a physical, but it is something that does exist.
It does exist.
Okay.
And with our enrollment table here now, once we've done this design-wise, you know, we noticed right away when we started our design, we have students, we have classes. We thought, well, that's a many-to-many relationship. We've got to resolve that with a link table. We're going to use the primary key of both tables as foreign keys in our link table, make that a composite key. And then all of a sudden we realized, oh, well, you know, we actually have data that belongs there because we have like maybe the semester that they enrolled. fall of 20, fall of 20, and maybe spring of 20 and fall of 19. And so we actually usually will end up finding that we have data elements that belong at that intersection of those two tables. There are probably other data elements in our data analysis that we will come up with that we would be able to add to that linked table. Those data elements that have to do with a student-specific enrollment, because that is something that ends up being an entity for us. So linked tables are really, really important because if there isn't an understanding of them, it is really easy to make a poorly designed database by trying to include data from another table in your table incorrectly.
I'm just kind of making like a connection between this and C#. So it's kind of like you can hard code stuff in, but it makes it harder when someone else has to come out.
Right.
So it's much easier to do. So that's kind of the table they're just taking out.
Exactly. And you'll see people, I don't know why, but people when they do design, they'll have these big meetings and they'll argue with each other and they'll say, 6, we're going to limit it to 6. They can only have 6 classes and we're going to carry those 6 classes on that student table because we don't need another table. People get really upset about it. I don't know, it's like it's going to cost them extra money or something. And they're like, no, we're not going to, we're going to do, but then yeah, just like Brady's saying, then now all of a sudden we have this unrealistic limit that's going to cause us trouble on down the road.
What if you need to add like can attend class at campus, like, or has the scary thing that's going around?
Yeah, so it's just illogical, but people will get that way in design meetings because new tables, when you're in a design meeting, there are people that act like that's going to cost $1 billion to add a table.
So I mean, but is that really the gist of the, when you get down to it, the problems in database management is you get maybe a bad design or a design that was good at the time, paradigm shifts over time, and now you have to go back and reevaluate, and that causes
a huge amount of the problem. And we're seeing as we create these things, just as you're creating diagrams, you're already seeing this time investment in the design. And you know, people, the more time they've already invested, the less willing they are to make change. And so even though we can run into a flaw before it's set in stone, we can still run into a lot of resistance to fix that problem because so much time has already been invested. But getting things designed properly is so important. Because if we don't use linked tables properly and we don't understand how meaningful that is in bringing our data relationships together, we can have a lot of problems. So that's an awesome concept for us. Now, when we're working with data, we want to eliminate redundancy. We saw that from those very first spreadsheets, right, where they said we have this salesperson's name repeated 7 times in our table, and we changed it, and now it doesn't match everywhere. So we don't want that redundant data. Sometimes people will say, having a foreign key is adding redundant data. That's not redundant data. That is meaningful data that's required to make the relationship work. If I don't have my link table carrying a student ID that does duplicate the student ID in my student table, I can't match them together. I have to carry that data in both places. So it's not redundant. So we just have to be aware that some of those arguments are only accurate when we're talking about data that is truly redundant, like somebody's name existing in 2 or 3 different tables. Here we see that we've got an invoice number and we have a customer, and for customers, we might have an invoice or a bill that we sent to that customer. So for one customer, we have many invoices or bills. Then for one bill, we could have several line items. You've seen this if you buy stuff at Amazon, right? The line item is each thing you buy. So if I buy 10 flash drives and external and all of those, each of those is a line item, and each of those line items has the number, the product code, how many I bought, the price, all that kind of great stuff. Well, my line item has to carry the invoice number, or else I don't know what invoice that thing belongs to. And my line item also is going to carry a product code so that I know that FJZ67 is my set of flash drives. So I can go to the product code table to find that. So we start seeing how that duplicated data is not redundancy. It's being able to make the connections from one piece of data to another. Now, when we're working with multiple keys, we might need an index. So if I look at my enrollment table, I know that sometimes I'm going to be wanting to get data from this table based on the course code, the class code, right? I know I'm looking for, yes, sir?
Before we move on,
No,
I have
sure.
one question about the relational table that I haven't been able to crack.
Uh-huh.
So in all of the examples I see, there's like an orange highlight on certain attributes, generally on a key, but it's only in one, and I'm just trying to figure out. I haven't figured it out of the book. But what does that orange highlight represent?
I think that's where the person who did the screenshots cursor was sitting.
I'm good with that.
Do you think that's it?
it?
I wondered that, and that's what I decided.
Okay. Thank you.
So if you guys come up with a deeper meaning, let me know, because that's where I'm sitting with it, is that the screenshot that was selected. Okay, so an index. I have all this data. And think about this link table. I could have millions of entries really easily, right? If I'm looking at a big school with a lot of different courses, and I have this table entry for every student and every course that they've taken, it could be quite huge. And I want to find all of the students who have taken CIS250. Well, in order to do that, the database management system is going to have to look at all of these class codes in that list. All of them, and just keep looking until it finds 250. Oh, here's one. Finds another 250. Oh, here's one. And it's going to be setting that off to the side, building the results for us. So that could be quite a horrendous table scan if I look through every single thing. Well, an index allows me to build pointers into my table so that I can access data based on its value quickly. So it's kind of a reference point. Oh, they don't give us a picture. I thought they did, sorry. Hang on, let me see if it was in the book. I lost my picture. There it is. So our actual table, in this case, we're looking at an art museum, and we have a table of paintings. So for every painting, we have its title and an idea of who painted it. And then the actual painting is given an ID also. So we have an index here that's set up into the painter number, because we might want a list of all paintings by a specific painter. And so our index, if you can see, is kind of this hidden table that's behind the scenes that we don't actually see. And in this hidden table, we have pointers that say painter number 123 can be found at position 1 and 2 and 4 in this table. And it's actually using pointers stored internally, pointers to specific pages in the disk file of the database, so that it knows where that actual record is saved, that row is saved within on the disk in the database. So these physical pointers are saved within the index file. So if I say I want all of the paintings by painter number 123, this index can be used, and the database management system can go directly to location 1, 2, and 4 to retrieve those results. My index then, if I were looking for painter number 126, would say the pointers for that painter are 3 and 5. And so this is a very, very high level view of what's going on with that index. But basically, it's a series of pointers that are saved on disk also in another location that allow us to quickly access data. So we can have an index, and we're usually going to end up telling the database management system that we want an index created on any foreign key. So the database management system is going to be building this pointer structure behind the scenes for us for every foreign key that we have. So if I'm looking at our enrollment table, I would have an index built on the student ID, and I would have an index built on the course ID. And that way I could quickly access each of those items. Now, indexes are something that we don't usually see, but they can actually cause a lot of performance overhead in our database management system. So when we start getting into using them in the real world, they start making a they make themselves known. And that's because every time I update a table, I have to update any associated indexes. So in our little course table, we already have 2, right? We have an index for our course code and an index for our student code. So when I add a new row to that table, I have to add that information to both of those indexes. If I update that table, the associated index would have to be updated. So we can cause some performance overhead on database updates if we have a lot of indexes. But they'll help us get to our data a lot easier. And that's, in a nutshell, all of COD's database rules. Let's look at them. Information. Rule number 1 from Dr. COD. Information in a relational database must be logically represented as column values in rows within tables. We must guarantee access. Every value in a table is guaranteed to be accessible. We need to handle null values. We need to know that they're different than empty or spaces. Nulls mean absolutely no value. We need to have a catalog or database dictionary that keeps track of the metadata, the information about how our tables are created. We need to have a sublanguage that's comprehensive, and that will be SQL that we'll see. We need to be able to update data through any view, and we'll understand that a little bit more as we get into that stuff. We need to be able to, at a high level, insert, update, and delete data. We need to not be dependent on the physical data storage. So you as a programmer should not have to care how much disk space the database management system is using. Physical data independence, we just don't care. We also need data independence in a logical way, meaning that if I update the database's definition, it doesn't affect the programs that are already developed that use it. We don't want to have to go out there and touch every program. We need to have integrity independence. That means that integrity constraints, those rules we have, must be definable to the database itself. And we saw that with our 3D animation, that we can declare something as a date, and then the database management system will make sure to guarantee that the integrity of that data. Now, distribution independence, our end users and our application program users should be unaffected by the location of our data. If I work for a company that has 50 locations, I should be able to get data from all of those locations without worrying about where it is. I shouldn't have to do 15 different connection strings to try to go get data from this location and that location. That's not the idea. Non-subversion. We don't let users bypass the integrity rules, no matter what. So even if we have a database administrator who's trying to store a record or a row that depends on a vendor that doesn't exist, they can't bypass that rule. They can't put in some sort of code that says, let me do this just this one time. No, we are non-subversive. We won't let them subvert the system. In Rule 0, all preceding rules are based on the notion that to be considered relational, a database must use its relational facilities exclusively for management. So what that means is I shouldn't be using my database management facilities for other purposes other than managing my data. So I don't want to be using it as like my sales system or something like that. That's all separate. Okay, that's it for our chapter. Phew, in time. You guys have some stuff to do. Some of these concepts, I really love the way our textbook is presenting them. In some of them, it seems like we are doing pretty good at understanding, and they'll come to us a little bit more solidly when we have a chance to use some SQL, some SQL, and things on there, which will happen. So great job. Let me know if you have any questions. Get all those labs done and out of your way. Any questions from our remote users? I hope you can hear everything. You guys have your Discord groups. I'm going to go ahead and stop the Zoom session.